The first lectures will be delivered by some of our principal investigators and chaired by Professor Harry Thaler. Ladies and gentlemen, please welcome Professor Thaler.
Good afternoon. I'd like to open up the afternoon session for the International Institute for Carbon Neutral Energy Research, the kickoff symposium. And it's really a great pleasure to witness this grand international effort to address, I think, one of the greatest challenges of this century, and that being achieving a carbon-free energy future. And I'm certainly very happy to be able to contribute my small part of all this. We're very fortunate to have a very good group of individuals to tell you about some of the exciting things coming forward. Our first speaker will be Professor Tatsumi Ishihara, who's here from Kyushu University. I've known him and his work for some years. He's done some remarkable work, come up with some new materials which are really entering into the industrial field. So it's a great pleasure to see science moving into technology. And I understand that he's also now gotten very interested not only in the fuel cell area, but also in photo-assisted splitting of water and conversion of that to hydrogen. So he will speak to us this afternoon, materials for high-temperature electrochemical devices.
Thank you for the introduction, Professor Thaler. My name is Ishihara. I will introduce the activity of our hydrogen production group in this I²CNER. We call this group as Artificial Photosynthesis Group, and this is a member of my groups. And today I would like to talk on the overview in my presentations, and further detail is by the Professor John Kilner followed me. And this is a total research area covered in this I²CNER, and where we are is here. And we are the central part of this concept of the I²CNER, and we use these kind of the energies as initial energies to produce hydrogens and the storage of the energy to the hydrogens and average of the energy to the hydrogens. And also there are a lot of the heat unused. Therefore, we also use the heat to convert to the hydrogens. As you may know, the hydrogen is expecting as a clean energy carriers, but unfortunately, hydrogen is not the clean. This is because hydrogen is now produced by the steam reforming reaction. Therefore, during the reaction, there are a lot of the carbon dioxide is byproduct and formed. That is why I say that the current hydrogen is not clean. And on the other hand, solar energy is only the infinite energy, and therefore, if we can convert and storage this solar energy as a hydrogen, then the society becomes very compatible with environment. Therefore, the issues to overcome in this group is to the development of the new concept of the photosynthesis type catalyst process and the new efficient water and CO2 electrolysis reactor with highly efficient solar cells. And this is a roadblock. And at the moment, as I mentioned, there are several number of the technologies proposed for this concept, but the problem is efficiency is so low. Therefore, we want to increase the efficiency for production of hydrogens. First of all, I would like to briefly introduce you what is a photosynthesis. In the natural photosynthesis, plant use solar and water and CO2 to form oxygen and sugar. But so the total reaction is expressed like this way. But unfortunately, photosynthesis does not give hydrogens, which is interest for energy carrier and also important in the future energy clean source. Therefore, we propose in this group to use solar as a primary energies, and water is another material source to produce hydrogen and oxygens. And in the natural photosynthesis, the product is only the proton, not the hydrogen. In order to obtain the hydrogen, we need to excite electron to the further higher levels. And the target value of these groups is to the conversion efficiency of the solar energy to the hydrogen higher than 10%. And I want to show you what the meaning of this 10%. The photosynthesis, there are many calculation ways to of the conversion efficiencies, but the almost 30% is the theoretical max and theoretical maximums. And for the case of the cone, just 1% is efficiency for the conversion of the solar energy to the final sugar product. Okay? That is why this 10% is really high value compared to the current photosynthesis systems. And as I mentioned, in the case of the plant, they use so-called Z-scheme type excitations, and they use two types of the organic dye, and irradiated solar energy to excite it to the some levels. But this level is not high enough for the production of hydrogens. In order to obtain the hydrogen, we further increase the higher level for the electron excitations. And therefore, we will apply the two types of the approach. One is a so-called photocatalyst. And this is a conventional photocatalyst systems. And in the case of the conventional photocatalyst, they only use the inorganic materials, and they use only the one excitations by photoenergies. And this excited electron is forwarded to the proton to form the hydrogen, and hole is forwarded to the OH to produce oxygen. But the roadblock of this technology is a very short life of the excited electron here. Therefore, before the pass it to the proton, this was disappeared. Okay? And compared to the, this one, that is why the efficiency of the current photocatalyst is as low as 0.01%, which is much lower than that of the conventional, that is of the present photosynthesis systems. And therefore, we propose newly on the combination of the organic semiconductor with organic semiconductor combination with the inorganic semiconductors. This is our preliminary prepared catalyst. We use the KTA03 as the central and covered with chromium tetraphenyl porphyrines. And by using the excited electron pass it to the chromium tetraphenyl porphyrines, we can successfully achieve this kind of the Z-shape excitation of the electrons. And this is a preliminary result of our groups. And as you see here, we observed hydrogen and oxygen from the waters. But this is a result of the formation rate. But this energy conversion efficiency was much higher than that of the conventional photocatalyst because the combination with these organic dyes, but still much smaller than that of the 0.1%. Therefore, we need to further increase the efficiency by optimizing of the catalyst. Therefore, in order to optimize the catalyst, there are several number of the issues we studied in this WPI project. Especially, we have to design the excited electron state by optimizing of the organic semiconductor and also using the narrowband inorganic semiconductors. In order to this, we need to assist by the quantum chemistries. Therefore, Professor Yoshizawa in the Kyushu University is also collaborated to us. And by adjusting over this system, we are targeted to the conversion efficiency higher than 1%. And furthermore, the realized systems for increasing the high efficiencies to the combination of the solar cell with that of the electrolyzers. And this is very simple calculations. For example, if the 11% of the conversion efficiency of solar cells and 90% of the electrolyzer, then we can easily achieve the 10%, which is much higher than that of the photocatalyst. And that is why we newly developed organic semiconductor type solar cells combined with steam electrolyzers. And the advantage of steam electrolyzer we'll introduce in the Professor Kirina's talk. But I briefly introduce the we applied two types of the electrolyzers. One is the oxide ion conductors electrolyzers, and the other is proton conducting electrolyzers. And the difference is which site is hydrogen obtained. In the case of proton, the water is electrolyzed to form the oxygens, and the hydrogen is permeated. And in the case of oxygen, water is electrolyzed to the oxygen is permeated. And if we combined with this system to the CO2, then the obtained product is slightly different. In the case of the oxide ion conductors, we obtain the CO and hydrogen, and then we can synthesis of the higher hydrocarbon by Fischer-Tropsch synthesis of the obtained synthesis gas. But in the case of the proton, we can obtain directly, we can change to the carbon dioxide to methanes. Therefore, this kind of the reactor is very interesting for recycling of hydrogens, recycling of the CO2s. And in order to develop these reactors, Professor Matsumoto in the Inamori Frontier Research Center will collaborate with us. And this is a relationship in our groups. As I mentioned, we use the primary energy as the solar, and materials of the water, or CO2 or the water, put it in. And there are the two types of the applications done. And then obtained hydrogen, the activated of the chemicals obtained from the CO2s. And we also can collaborate to the tripology groups, and also the fuel cell groups, and also CO2 captures group. And these are the different groups in this WPI project. So thank you very much for your kind attention.
Now I'd like to introduce the second half of this team. This is Professor John Kilner, the Brian Steele Professor of Energy Materials from Imperial College. He was recently department head and dean of the Royal School of Mines. A good friend of mine and colleague who's done excellent work in the field of ionic and mixed conductors and has made major contributions to the field of solid-state ionics. Professor Kilner.
Thank you very much indeed, Harry, and it's a great pleasure to be here today to give this short talk on the work that I intend to do as part of this I²CNER. I must say I do like the name, and there is a good reason for that, because I come from Imperial College, which is known as IC, so the first part is from where I work, and if you notice, the NER is the last part of my name, so I think this was actually made for me. Okay, we're going to talk about electrolysis, and of course, as all of you know, electrolysis is not a new technology. It's been around since the 18th century. In fact, playing with electrolysis systems such as this is a schematic from a high school experiment just showing that by breaking up water electrochemically, you produce oxygen and hydrogen. By playing around with systems such as this, Sir William Grove devised the fuel cell. So one can buy water electrolyzers, and their state-of-the-art are the ones that do the electrolysis of liquid water. The efficiency is very important. Electricity makes up 2/3 of the cost of the electrolysis plant. And the low operation temperature leads to high electric power consumption. I'll explain here. Here we've got a chart of temperature versus the specific energy. This is kilowatt hours per cubic meter of hydrogen. And this is the total energy demand. This is liquid water, and this is, of course, steam. And one could break that down in the electrolysis process into the electrical energy demand and the heat demand. And you can see as we rise in temperature, most people in steam electrolysis are working between 800 and 1,000 degrees centigrade. The electrical demand is greatly reduced. And that, of course, is because we're getting some of the energy from the heat of the process. So how do we get into this regime, and how do we make steam electrolyzers? Well, Tatsumi has actually introduced this a little bit into his slides. The way is in the same way that we make a solid oxide fuel cell. We take a ceramic membrane, and we can have two types. We can have a ceramic membrane that's an oxide ion conductor or a protonic conductor. We then use usually mixed conducting oxides as the electrodes. And then, of course, we connect this up to a source of electrical power to electrolyze the water. Here are the electrode reactions that are gone in the oxide ion conducting case, where the hydrogen is produced at the cathode. And will be mixed, of course, with some unused water, so that has to be separated out. One of the nice things about using proton conductors is that the hydrogen is evolved at the cathode again, and we see that only hydrogen is produced. And here are the overall cell reactions there. We're initially going to focus on the oxide ion conducting electrolyzer because of the material sets for either the oxide ion conductors or the proton conductors. The oxide ion ones are far more advanced. So that is the area that we'll start in. So what are the advantages of going to high temperature steam electrolysis? Well, we've just seen that we can produce hydrogen with a low electric power demand. As Tatsumi says, we can utilize waste heat. That can be either industrial waste heat or waste heat from a nuclear power station. There are the other applications, CO2 electrolysis. In fact, NASA had quite a program on CO2 electrolysis at one time. That was because electrolysis was going to be used from the Martian atmosphere to provide oxygen for the life support for the crew, and CO, which could be used in a fuel in the spacecraft. And this is something that is gaining quite some interest in Europe. That is the co-electrolysis of steam and water to produce syngas. But one of the other advantages of these high temperature cells is they have good reversibility, so we can use it for storage of energy. We use the electrolyzer to produce the hydrogen, put it in reverse, and as a fuel cell to produce electricity when demand is high. One further advantage, and it is an advantage of all electrolyzers, is they produce very pure hydrogen, which is very suitable for automotive applications. Let's just look at the reversibility. Here we have IV curves. This is the cell potential versus current density. This is when the cells are acting in fuel cell mode. This is when they're acting in electrolyzer mode. And for the low temperature cell, it's the green dashed line, and for the high temperature cell, it's the continuous black line. And you see that the high temperature cell is actually continuous across the divide from working in fuel cell mode to electrolyzer mode. But for the low temperature cells, there's about a half a volt jump here, caused by problems at the electrodes, really at those low temperatures. So it's a much more efficient system, a much more reversible system at high temperatures. There has been some research so far into high temperature electrolyzers, mainly on zirconia-based systems, which means that the cells must be operated in this temperature range of 800 to 1,000. And that causes engineering problems in the fabrication of devices. There are problems with sealing at these high temperatures, problem of thermal stability of the materials. Also problems with thermal cycling up and down to such high temperatures, and really no one has achieved useful operational lives with thermal cycling so far. The materials cost is also very high. We have for balance of plant, for interconnectors, we're having to use expensive materials. And one of the real problems is that most studies have showed very high degradation rates. And these degradation rates can be 2 to 3% per 1,000 hours of operation. And really, to get into commercial operation, we need to get those down, initially at least, by a factor of 10. And the sort of things that happen is that we can get delamination of components. This is a part of a cell. Here's the electrolyte, and here's the cathode. And simply, this, by the evolution of oxygen, we've almost blown that cathode away from the electrolyte. And here's a cell that actually we were working on with colleagues at Imperial College. This was a tubular cell, and again, at high current densities, we created so much gas that we delaminated the system. So we need to find strategies to get rid of these bottlenecks to the development of these high-temperature cells. And the way forward is really to move to intermediate temperatures. And by intermediate temperatures, I mean as defined by the high-temperature electrochemistry community, so some of you might not find less than 700 degrees centigrade an intermediate temperature. But in this temperature range, we have better material stability, easier gas sealing. When we get down to, say, 6 to 500, we can use stainless steel and compression gaskets to seal, cheap metal interconnects, more rapid startup, shutdown, and actually good stability during thermal cycling. And low temperature, of course, always means lower corrosion rates. So here are the things that improve as we go down in temperature. We improve durability, we improve cost, and we improve manufacturability. But unfortunately, there are things that, like the high temperature, the electrodes work much better at high temperature, the electrode kinetics are faster, and of course, as we saw, we reduce the electricity demand. So what we need to do is to find a temperature range here, a sweet spot really where these electrolyzers will work efficiently, durably, and be cost effective, an optimum temperature range. And I believe that this is between 700 and 500 degrees centigrade. So to do this, we're going to need some new materials, and this will be the basis of most of the work. And the materials will be developed by taking the selection criteria, doing bulk experimentation, electrochemical measurements on cells, also developing materials by using ab initio so atomistic simulation, molecular dynamics, ab initio calculations, to find materials where oxygen moves freely. And those will be the sort of materials that will give good performance in these cells. Also, what's very important is understanding what's on the surface, because that's where all the electrochemical activity takes place. And as part of the work, I intend to do work at Imperial College on materials developed here, looking at their surface structure. So just before I finish, I'll give you an example of some of the sorts of materials we've been thinking about. These are mixed conducting materials which would be used as electrodes in these cells. These here are Ruddleston popper phasers, they are called, and they consist of layers of rock salt here, and perovskite materials, rock salt and perovskite. So in fact, they're almost two crystal structures placed one on top of the other. This is an example of two perovskite materials, and these materials have high oxygen mobility at low temperature, and this is perhaps because I believe they are natural nanostructures. They're nanostructures that nature made rather than man-made structures. That's really all I'm going to say for today, and that's the sort of area that we'll be starting off when we start the program of new materials for these electrolyzers. Thank you very much for your attention.
Thank you, Professor Kilner. I forgot to mention that not only is he a good academic, but there's a company that's been spun off that's developing solid oxide fuel cells, Ceres Power, and I think British Gas has recently started to implement some of those cells. So, congratulations.
Yeah, we've got cells out. Well, we've got units out now on test.
Great. Any quick questions? If not, let's thank Professor Kilner again. So we'll welcome our next speaker, Professor Dr. Etsuo Akiba, who's a faculty member here in Kyushu University. He's the head of the Hydrogen Storage Materials Division and principal researcher of this new institute. He's worked extensively over the years in hydrogen storage material, has developed some important Lave phase solid solutions, which have some of the largest hydrogen capacities for practical onboard applications. And he's received a number of prestigious awards, including the Herbert Brown Award for Innovations in Hydrogen Research recently in 2008, and the I²CNER Technical Achievement Award in 2010. So he will be one of the two speakers who talk to us about the future of energy and storage. Thank you.
Thank you very much for kind introduction. Today I'd like to introduce briefly about activities of division of hydrogen storage materials. So this is an organization map. our division is here. Those are our PIs, 4 PIs. All of them are here to attend this kickoff meeting. Before introducing our activities, I would like to show you one statement only a few weeks ago given by our industry. That is a joint statement by private companies concerning the introduction of fuel cell vehicles onto the domestic market and the development of hydrogen supply infrastructure. So this is a little bit busy chart, so just I summarize here. This is a scenario given by our industry for market penetration of fuel cell vehicles and hydrogen refueling stations. And this is summarized in numbers. July last year, our industry told us by 2025, fuel cell vehicles will be 2 million, and refueling station will be 1,000. And a few weeks ago, our industry again told us fuel cell vehicles will be produced 1,000 to 3,000 per year by 2015. And before that, refueling station will be installed in Japan about 100. So under this situation, hydrogen storage, especially on board, is a critical issue to realize the hydrogen economy. So this is a roadblock of hydrogen storage and transportation. This is a very, very critical issue for the hydrogen economy because volume energy density of hydrogen is just 1/3,000th of gasoline. So it's very difficult to overcome such a 3 orders magnitude of difference by a simple technology. So this is a roadblock and hydrogen storage and transportation. And at present, there is no appropriate method of hydrogen storage and transportation that satisfy following requirement simultaneously. Those are volume energy density and weight energy density, energy efficiency, and cost. Those are targets set by NEDO Japan by 2020. And I would like to emphasize hydrogen storage materials are one of the most promising candidates for hydrogen storage and transportation system. And this is just one view graph to tell you our technical approach and target. We carefully select most possible candidates of high-performance materials. Those are magnesium-based materials, lithium-based materials, complex hydrides, hydrogen absorbent, and combination or composite of these materials. So you can easily to recognize those metals, alloys, inorganic materials, organic materials, carbon, and etc., etc. And we are very lucky, and also I'm very much excited because we have a lot of good chemists inside of I²CNER. And I'm very much excited to collaborate with them to run a chemical way of thinking and also how to synthesize new and advanced materials for hydrogen storage and transportation. And also, before developing advanced materials, we have to understand hydrogen metal or hydrogen material systems using various methods, including in situ measurement. In situ means under hydrogen atmosphere. We should observe what happens. So we will use a neutron and X-ray, Raman, animal, and etc., etc. This is one of the good examples. This is a NOVA, neutron total scattering machine installed in JPEG. JPEG is one of the strongest neutron sources in the world. And we installed this machine especially for hydrogen storage materials. This equipped with an in situ hydrogen reaction vessel, so therefore we can observe behavior of hydrogen inside the materials using this machine. And also we measure storage performance of materials developed, and also we collaborate with the modeling people to understand what happens inside of materials. And based on those our scientific investigations, we will develop high-performance materials. And our target is 68% as a system, as I shown you NEEDO 2020 target. This is only one slide to show you a scientific part. We recently observed a single hydrogen atom in the vanadium hydride using transmission electron microscope. If you look at the textbook, transmission electron microscope cannot observe hydrogen atom. But firstly, in the world, we observed. And this kind of technique can be useful for not only for hydrogen material, but for example, hydrogen-compatible materials and other materials. And also, we are very much excited to use this kind of technique with my colleagues inside and also outside of I²CNER to understand hydrogen behavior. Thank you very much.
Thank you, Professor Akiba. And now we have the next part of this team. It's my pleasure to introduce Professor Dr. Louis Schlappach, who's associated with the Swiss Federal Institute of Technology in Zurich. He was trained as a solid-state physicist, but has had a continuing interest in hydrogen storage in intermetallic materials, done extensive work in surface science, and aside being professor, he's also been the CEO of EMPA, the materials platform for the ETH. So it's with great pleasure that I introduce Professor Schlappach.
Thank you very much. It's a great pleasure for me to be involved in the building up phase of that new I²CNER, which is a great program. As I'm Professor Emeritus, you certainly also allow me to ask questions, for example, question whether we set priorities right. So at ETH, I'm Emeritus, and I have an involvement also at NIMS in Tsukuba, where I spend a couple of weeks per year. And in Switzerland, I'm still managing a new research program for 5 years in the field of smart materials. We know that we did not participate up in that space experiment, but we know that the society has certain needs with respect to materials and energy. We want to have a support for our health, for buildings, for communication, for mobility and transport, and we should try to do it in a sustainable way, kind of looking for harmony between mankind, nature, material, economy, and industry. That's a big challenge. That is an idealized image how we think it could be. Going back also a little bit to Thales of Miletus, of course not the car, not the fuel cell car, but that is much more reality, far from sustainability. Though we have problems because heating, air conditioning of buildings, mobility of persons, transport of goods, they contribute to the quality of life, but they also cause emissions, low air quality, global warming, climate change, and things like that. We have problems, and we are scientists and engineers. We have to solve problems of the society. What we have seen in presentations of, with recent data this morning by our colleague Finley, was already realized a long time ago, for example, by Arrhenius. Arrhenius already noticed that there is a strict correlation between fluctuations of CO2 and fluctuations of the temperature. That is quite an old knowledge. And the newer one is certainly that temperature started to increase. Consequences are manifold. Floodings not only in Brisbane, also in Switzerland, and glaciers, for example, in Alps in different countries also retract very, very considerably. Alps get smaller and smaller, and maybe if we continue in 20 years or 30 years from now, Switzerland won't be a winter sport country anymore. let's have a little bit a broader look at the situation. Efficient use of energy and materials in intelligent systems is certainly an issue. And when we look in industrialized countries, we spend something like 40% or more of our energy consumption in buildings, probably 30 to 35% in mobility and transport, and about less than 30% in processing, making of goods. And for reasons I do not understand, but in Europe, in Asia, and in Japan, the focus now in order to reduce CO2 is only on mobility. And I hope to show you a little bit that it would be much easier, energetically interesting, economically interesting, to look at the buildings. Technologies are known to reduce the energy consumption and CO2 emission in buildings. And that is not an issue, unfortunately. Here are some figures concerning Switzerland. That's the time scale, and that's the energy consumed in kilowatt hours per square meter and per year of apartments. And you see when we went into the oil periods, that increased a little bit, but due to strict legislation after 75, that decreased enormously, more than an order of magnitude. And that is now by legislation. I'll show you a new building. It's a sister institution of EMPA, an Institute for Global Water Research, and that is almost a zero energy building. Let's have a look at this beautiful hall, lecture hall. Has very good acoustics, good light engineering, has a good design. But when you look at the quality of the window, when you look at the quality of the engineering of the windows, including the iron frame, it's not the solution we should choose in the year 2010 or 2011. In that building here, which is energy-wise really very modern, also design inside to see ordinary working rooms, library, a big entrance hall. And the energy sources are all persons working in there, like we today, 100 watt power. The IT server, PV panels on the roof, thermal collectors, and an airflow with night cooling. And that leads to an almost zero energy technology, which is feasible. And with that, that's the easiest way to reduce CO2 consumption. But it goes only through legislation. That's a perspective of the potential in the building sector. You see, blue is oil, so CO2 related, and there would be good chances, in fact, within the next 15, 20 years to reduce the oil consumption very, very, very considerable, and that would be of great help, and that would be much simpler than to convert, than to go to clean cars, to clean mobility. Okay, let's go closer to the subject of I²CNER. Why hydrogen? Well, we are talking of energy and heat power, which is, of course, linked to the laws of physics. And we have four interactions or four forces: gravitation, weak nuclear, that's somehow a computer problem, electromagnetic or Coulomb interaction, and strong nuclear. And when we look at the mass to energy ratios which are involved, let's say gravitation is 1, then electromagnetic is 38 orders of magnitude better. That is why when we want to need gravitational forces, we need large, large quantities. Hydropower needs large, large quantities. Electromagnetic, 38 orders of magnitude better, and strong nuclear power would still be 2 orders of magnitude better with respect to mass. And that's, of course, the way we use its application. So in the future now, I will talk about electromagnetic or chemical energy, though where only electron and differences in electron energies are involved. The properties of hydrogen: first of all, it's a non-toxic carbon-free electron gas, and it is available in non-limited amounts, but in the form of water and not of energy, so it's not the primary energy, of course. But it has, for chemical energy carriers, very important, it has the best ratio of valence electrons to nucleons. no neutrons are involved, no neutrons are involved at all. That makes 1 electron per proton, and the electron binding 13 electron volts binding energy. That's the best chemical energy carrier. Then isotopes exist, but it is a molecular gas at room temperature, can be liquefied, can be solidified. It's at very low temperatures and under pressure, probably a metallic system, maybe even a superconductor. Hydrogen production is a topic in many conferences up here, though I'll quickly go through it. We need a primary energy source, renewable or nuclear. We make electrolysis. We just heard about high temperature issues of the electrolysis and how instead of using electricity only, you can also bring in the energy by heat. And then you can make kind of a closed system apart from that income and from that energy output here, where you transport, store hydrogen, you bring it back in the form of oxygen. Well, the use of hydrogen then, of course, would be we burn it with hydrogen in a combustion engine in order to get water and heat, or we kind of burn it in a fuel cell in a direct electron transition, and we get electricity in addition to water. Sorry, some arrows are missing here. So why do we don't use that very comfortable situation? It's of course because it is an ideal gas at room temperature. So 1 mole of hydrogen, only 2 grams, has a lot of energy, but it takes 22 liters of volume. So it has to be compacted by something like 3 orders of magnitude, and that is an issue. So an overview about compacting techniques. We have heard about high pressure, typical tanks of 200 bar, high pressure tanks with aluminum inliner with carbon fiber reinforcement, up to 700 bar or 70 megapascal, working at room temperature. There are cryo techniques, liquid hydrogen, where of course you lose a significant part of the hydrogen chemical energy in the cooling and para-ortho separation process, and you need of course cryogenic techniques in order to keep it. You can use, and we'll talk a little bit more about that, the absorbed hydrogen in the form of chemically bound, so dissociated hydrogen atoms stored somehow on interstitial sites in lattices of solids, and that has a good reversibility, but some other disadvantages, as we will see. And the last possibility is to physisorb hydrogen on high surface energy materials, but again, physisorption needs cryogenic temperatures, at least liquid nitrogen, because physisorption is very, very weak. The high pressure system, the pressurization, has its limits. You see, of course, we know in an ideal gas, when you double the pressure, you diminish the volume by half, but for all real gases, this does not hold. The deviation from the ideal gas behavior due to the eigenvolume of the hydrogen atoms or molecules becomes very significant, already above 500 bar pressure, and it does not make sense to go much higher than the 700 bars or 70 megapascals used today. So that's a natural upper limit. Though with simple words, the 2 possibilities are physisorption of molecular hydrogen on high porosity, high specific surface area materials. And today, no materials are known which do that in a reversible way around room temperature. Cooling is needed. The other way is chemisorption, so the dissociation of hydrogen molecules at the surface by specific catalytic Brunn processes, and the dissolution and metal hydride or solid hydride formation in an ordered or in a disordered way, where of course the enthalpy of that solution or of the hydride formation dictates with a lot of thermodynamics behind it, at which temperatures the process is reversible. A typical system could be characterized like that. You have a hydrogen gas phase. The hydrogen molecules are dissociated at the surface and diffuse as hydrogen atoms to make a solid solution phase, and at higher concentration, a solid hydrogen compound or alloy. And of course described by a typical phase diagram, which I will not explain here. There is also an electrochemical way. You start with an alkaline electrolyte. You bring water molecules to the surface. You split them into OH minus, which remains in the liquid, and adsorb protons. And you add an electron through the bulk in a charging process to get the adsorbed hydrogen species, which goes into the system again, and where you cannot distinguish whether it entered that way or it entered through the electrochemical way. Both processes are reversible, and that process here is used in rechargeable electrodes, and Prius, also the third generation, runs on batteries which are based on that principle using AB5 type metal hydrides. Though here we have physisorption and then chemisorption, here again physisorption, chemisorption, diffusion, intercalation. That is an old picture of a nice article we had a long time ago in Nature, which shows a little bit the volumetric behavior when you need a couple of kilograms of hydrogen for a mid-sized, well, European mid-sized car to run something like 500 kilometers. And here, an illustration of very, very many applications of liquid or solid-state stored hydrogen. I'm not sure what is known here, where you have the building and the activity heterogeneous, that Daimler Chrysler had a prototype car, H600, hydrogen-driven, combined with a lithium-type battery, which they named Genius also. Okay, there are many solids which react with hydrogen under pressure at reasonable temperatures, and you can get hydrogen mass contents much above the 4, 5, 6 weight percent which are told, but the kinetic or thermodynamic reversibility concentrations are not yet where they should be. Though in that sense, the results of today's of the last 20 years of hydrogen metal hydride storage or hydrogen solid-state storage systems are somehow disappointing. There's a lot to do, and probably it's correct to go back to fundamental science in that field. Though borohydrides intervened also, and we have one participant in our group, Ping Chen, sitting down there, which also looks into amides, so nitrogen-containing systems. Well, illustrations which are known. And here, the potential for the substitution of oil in the field of mobility is much worse than for its potential in the field of building. So probably it will take, of course, it will diminish. Fuel cell vehicles and other vehicles will diminish the oil consumption, but it might last another 40 to 50 years until we can reduce it more or less completely. There are many ideas around how hydrogen storage by solids could be improved. Theoretical approaches by computational material science, but also very many experimental approaches. Here just an illustration for the decoration of carbon nanostructures by titanium, which would help to absorb hydrogen. Porous metal-organic frameworks, zeolites, where again you'd have to introduce certain materials to bind hydrogen strongly. Let me spend a very few minutes on hydrogen and its safety. We all know that the explosion limits start around a few percent and go up to in the rich limit up to about 70 volume percent hydrogen in air, though that is a big advantage. In fact, you can run a combustion engine with a very, very lean mixture. We all know that, well, not everybody knows that Zeppelins run around the world, not just until an accident for a few years. In fact, the first Zeppelin was up in the air in 1900. And the accident with the Hindenburg was 1937. So more than 30 years, many Zeppelins did a lot of nice traveling with passengers all around the world. They flew over Europe, over the United States, over Japan back. It's, and today we remember just that Hindenburg burned. And the cause of the fire, in fact, was not the hydrogen, because you have seen in the pictures from the color, it was mostly the skin which burned. At that time, polymeric skins were not yet available, so these were highly inflammable skins which had been used there. Aspects of hydrogen safety here, that is a hydrogen-fueled car with the fuel down here, and of course, hydrogen as a light gas. If it has a chance to escape, it goes up into the air, and whereas gasoline is a little bit more dangerous. I'd like to talk shortly about another risk. Lavoisier in France was very, very strongly in the development of new chemistry, and his wife helped him sometimes, and he was the discoverer and revolutionary of very many things. Among others, he was the first to show that water is not an element, but water is composed of two different materials, and he called the name hydrogen and oxygen. He named them. Lavoisier worked before French Revolution and was kind of as a tax collector. He got his money to live. His science he had to pay himself. So we have to recognize how generous the Japanese government is today towards us in financing all that. So Lavoisier had to be tax collector. And as a tax collector, he ran into big troubles during the French Revolution. Here, the soldiers come into his laboratory. He was made a prisoner, and he had to go to the guillotine, and he was made one head shorter. Of course, not because of the hydrogen he had invented, but he had, as a tax collector, initiated the construction of a wall all around Paris to control much better the input and output of marchandises in order to increase taxes. I probably have to skip that. Okay, a vision for mobility, and I think that's important here at all, has to be light structures, not 2.5 mid-size cars. Light structures, that should also hold for DOE, sorry to say that. And, of course, efficient energy storage. And I'm very glad to show you here a picture that is a very light aircraft which was built in Switzerland and which should fly around the world, solar-powered only. And this is during a night. That's the moon. It has lithium electric power storage and a lot of photovoltaic cells. So it flew during a full day with sunshine, and it continued to fly all night thanks to solar power stored in there. Okay. So as a summary, for energy and mankind, of course, we have to follow physical forces interactions, thermodynamics, material systems, economic sustainability, time constants of production and use. But there are also social science effects, the acceptance of new energy technologies, for example, in buildings or lightweight cars by society. That is what we need in order to maintain or reach that harmony. And I wish you, I²CNER, good luck, very good ideas to all scientists and engineers working there in order to keep that harmony. Thank you.
Thank you very much, Professor Schlappbach, for a very nice integrated overview of the hydrogen economy and the hydrogen issues and problems. Thank you again. So we'll now go on to our next speaker, who is Professor Setsuo Yanagi. He is director of the Research Institute for Applied Mechanics here at Kyushu University, an expert in oceanography. In fact, has written several books in that area, Coastal Oceanography by Kluwer, 1989, and Satumi, New Concept for Coastal Sea Management. And Professor Yanagi will speak about carbon capture and sequestration in the ocean.
Thank you, Mr. Chairman. My title is Carbon Capture and Sequestration in the Ocean. Yes. So this is our main goal is to understand the long-term behavior of CO2, carbon dioxide, and the environmental impact of acidification to the ocean, and provide scientific assessment for public perception of deep ocean sequestration. Okay. The big barrier of our activity is the London Convention. Ocean dumping of carbon dioxide is itself prohibited by the London Convention. However, the carbon dioxide storage in the rock, that means geological CCS under the seabed, was permitted after the long scientific discussion in 2006. So therefore, the possibility exists for the permission of the carbon dioxide storage and sequestration in the deep ocean by the successful scientific assessment. So this is the image of the deep ocean CCS. We capture the carbon dioxide from power plant factories and change it into liquid and transport to the deep ocean, and then using a long pipe, we sequestrate the carbon dioxide in the hollow and more than 3,000 meters. So in the deep ocean, the liquid CO2 generates carbon dioxide hydrate film between seawater and the CO2. The most important scientific problem is how much liquid CO2 will diffuse across the hydrate film to the ocean. It's the biggest scientific problem. And the current and some turbulence. So this is a laboratory experiment in the National Maritime Research Institute. More than 300 hectopascal correspond to the 3,000 meters. The liquid CO2 is injected through the pipe and then make a bubble and sink to the bottom of the tank, and then aggregate and make the CO2 hydrate like this. So we plan to carry out the field experiment at the center of the Japan Sea. The depth is more than 3,000 meters. We call Yamato Basin. Okay? So this part is our planned area for the field experiment. So we developed the numerical model in Japan Ocean. And this is the result of surface layer. Surface layer is very strong. Current exists more than 50 centimeters per second, and so many eddies. The red part shows the warm surface water temperature and cold water temperature. But in the deep ocean, drastically change surface condition. This is the transect along PM line, summers and winters. Only the upper 200 to 300 meters seasonal variation exists, but deeper than 300 meters, main part is occupied by very cold, less than 1 degree Celsius waters we call Japan Sea proper water. The average residence time of this deep water is more than 100 years. Okay? So this, I skip this one. As for the current in the deep ocean, our colleague, Dr. Senju, summarized the field mooring result. This is like this. And then, based on these observed results, he draws such a schematic view. In average, counterclockwise circulation exists in the deep ocean of Japan Sea. And in recently, the PARES is developed, and then these operators continue to observe the mid-layers and deep layers current system in Japan Sea. So from observation of PARES, we can get such a spaghetti diagram. This is a trajectory of the drifting buoy. From the these data, we can draw such a schematic view of the current system. This result is very similar to the Senju's schematic view. So another my colleague conducted a direct mooring current measurement at this point. of large stock, nearly 1 year from 1994 to 1995. From this year, you can understand the current variation is near the same from the surface and to the deep layer like this. And in March, April, very strong current, larger than 10 centimeters current exists in very deep layers at this position. So from the summary of such a current meters, we can draw the seasonal variation from January to December in this part of the Japan Sea, bigger at 3 centimeters per second and 1.5 centimeters per second. Similarly, we can summarize the drifting V, ARGO, we call ARGO, drifting V current measurement like this, very similar result obtained. Such a seasonal variation is dominant in the deep part of the Japan Sea. So when we divide the northern part and southern part, ARGO flows and direct current measurement, a little different quantitatively, but similar seasonal variation is obtained. So to get the numerical simulation, we developed the real motion model, hydrodynamic model like this, 3D, 1.6 degree horizontal, just a moment, breeze size, and vertically we divide 46 vertical levels. And then using momentum equation, the vector diffusion equation of temperatures, and the parameterization of the interaction, bottom slope and density stratification, and then we calculate, obtain such a calculated result in deep ocean, the current in the Japan Sea, and then we can average current schematically like this, very similar to the Paris float and the direct mooring result. And quantitative comparison observed current velocities and model velocity, different parameterization, and then we can determine this parameterization is the best. Okay? So this is calculate the seasonal variations of the deep current, and this is Paris result and direct mooring, and then this is another parameterization, very conventional method. Our method is very good when compare calculation result and observed result. So this is seasonal variation August, September, October deep current system in the Japan Sea. Our target area is here. So based on this general circulation model and the fundamental liquid CO2 and CO2 hydrate and combine such a fundamental system to this general circulation model, we have to forecast the acidification in the Japan Sea, because acidification due to the injection of the CO2 in seawaters, chemical balance induced the dissolution of the calcium carbonate. That means the phytoplankton with carbonate shell and coral reef will be dissolved under the effect of the acidification. So this is a very serious program for the impact of the ocean CCS. So at the same time, we have to monitor the pH and partial pressure of the carbon dioxide. We already developed such a underwater marine system using such a glider underwater vehicle. Okay? So this is a roadmap of our first 3 years project. So based on this fundamental technique and scientific result, we want to develop the coupled models and the monitoring systems, and then evaluate the necessary cost of the ocean CCS. Thank you very much.
Thank you very much, Professor Yanagi. And we'll now move on to the last speaker of this session, Dr. Brian Summerday from the Sandia National Laboratories. He's a member of the Physical and Engineering Sciences Center, and he specializes in the scientific analysis and evaluation of the effects of hydrogen on metallic materials.
Thank you.
Summerday.
So there are, I think, certain unenviable positions to have during a presentation schedule, and one of them is being the last speaker in the afternoon before the break, especially when the break is supposed to be starting in 2 minutes. But I promise you that I have 9 slides, and that includes the title and the summary. You can count along with me if you'd like. So first of all, I'd like to thank Director Sofranis and Professor Murakami for inviting me to be a part of this I²CNER project. It really is a privilege. And I just wanted to mention that I'm representing the structural materials thematic area today. And this, the talk I'll be giving today really focuses on hydrogen embrittlement, but this thematic area is not all about hydrogen embrittlement, it also includes tribology. But I decided to go into a little bit of depth today and not cover the full range of activities that might be in this thematic area. So you'll see that this talk is very complementary to the talk that Professor Ritchie gave this morning. And in my own mind, I was thinking, well, Professor Ritchie's just the opening act here, so this is the main event. I really wanted to say that, Rob. So. And I chose this title very mindfully, this word improving. And Professor Ritchie made a number of comments this morning that I really appreciated. And one of them was the idea that the goal is not to try to develop materials that are immune to hydrogen embrittlement. This is probably just simply unrealistic, especially given all the windows of variables that can promote hydrogen embrittlement. But I do wonder, or one of the questions that I'm asking today that I think this thematic area needs to consider is, can we at least improve, in this case, the hydrogen-assisted fatigue crack susceptibility of technologically important materials such as low-cost ferritic steels? I wanted to give a number of slides that give some background. I know this is a rather diverse audience, and so I thought I would give just some help to provide some fundamental understanding of one of the central issues that I wanted to talk about today. And again, one of the comments that Professor Ritchie made today is that there's a very clear technology driver for this interest in hydrogen embrittlement, and that's one of the reasons why I enjoy this area of research, is that the science is really driven by technology. And the technology driver for hydrogen embrittlement really is about safety. And this is what Professor Ritchie mentioned this morning. And to illustrate why hydrogen embrittlement has to be considered from a safety perspective, if we consider a hydrogen containment structure like a pressure vessel or a pipeline, as Professor Ritchie mentioned this morning, invariably these components are going to be subjected to pressure cycling. And this pressure cycling can enable fatigue crack growth. And so if we just think about a cross-section through some cylindrical component like a pressure vessel or a pipeline, which I'm representing down here in the lower left corner, if this is subjected to pressure cycling, particularly in the presence of hydrogen, cracks can start to grow in the walls of these structures. And as I'm representing schematically in the upper left, if we were to monitor the amount that this crack grows as a function of the number of pressure cycles, the crack will indeed grow faster in hydrogen than it will in some inert gas like natural gas or even nitrogen. And so hydrogen embrittlement is very important from a structural integrity perspective of these hydrogen containment components. And as Professor Ritchie mentioned this morning, we're very interested in using common steels, low-cost steels. And so some of these materials happen to be very susceptible to hydrogen embrittlement. And that's what I'm illustrating here on this slide. So I'm showing you here some data. It's very similar to what Professor Ritchie showed you this morning, but this data was just generated in the last few months at San Diego National Labs, and a capability that we have for testing materials in high-pressure hydrogen gas, much like those that are here at Kyushu University. And what I'm showing you is a plot of this crack growth rate, the amount the crack grows per unit per stress cycle or per pressure cycle, versus this stress range, or as Professor Ritchie introduced this morning, the stress intensity factor range. And we do this testing on these model coupons that are extracted from materials where we can conveniently apply loads and measure displacements. And so if we measure this amount of crack growth per unit, amount of crack growth per stress cycle, you can see that for the tests that were done in high-pressure hydrogen gas, in this case 21 megapascal hydrogen gas, this is a low-cost steel that's designated as X52. It's used in pipelines in the United States. You can see that at some critical value of KT max, these crack growth rates start to increase quite dramatically. And these crack growth rates ultimately can be about 10 to 100 times faster than the rates in air. So you can imagine that these cracks can be propagating through the walls of pressure vessels and pipelines much more rapidly than they would in an inert environment, and this is a concern for structural integrity. If we were to look at the microscopic structure of how this crack propagates, and one of the common ways of doing that is with scanning electron microscopes. And if we were looking at this crack propagating from the side, if we actually were to look this way, if we were to break the specimen open and we look down on the surface, we can look at the microscopic details of how these cracks propagate. And as Professor Ritchie was talking about this morning, these cracks in these low-strength ferritic steels can actually propagate along grain boundaries, and I'll explain what that means on the next slide. But this is a very different fracture mode than what we would see in air. And so one of the emphases I think that we could develop in this thematic area is if we're going to improve the fatigue crack growth resistance of these low-cost ferritic steels and hydrogen, we need to understand this intergranular fracture phenomenon. And so let me just introduce what does this mean? It's intergranular fracture. Metals are composed of atoms that are arranged in periodic arrays. So imagine that the atoms are arranged on a lattice, which is not so different than the lattice you see on the front of this podium, but it's in 3 dimensions. And these atoms have a particular orientation, but not a uniform orientation. So the atom orientations might have different domains. And so these domains of a constant crystal orientation we call grains. And I'm just representing these grains like many material scientists do as hexagons. And so across these grain boundaries, the atoms have different orientations. And so what can happen, especially in the presence of hydrogen, is that hydrogen can segregate to these grain boundaries. And then hydrogen, one of the hypotheses is that hydrogen weakens the bonding across these grain boundaries and cracks can form at these grain boundaries. This is at least an accepted hypothesis for why we get cracks along grain boundaries in the presence of hydrogen. But we really don't understand a lot about this process, particularly under this action of the cyclic deformation. And so I think 2 of the questions that we can try to address in this thematic area is why does hydrogen-induced intergranular fracture in these low-strength, low-cost steels happen? Why does it propagate along the grain boundaries, especially under the action of this cyclic stress or the cyclic deformation? And then and a related question is, can we try to mitigate this intergranular fracture to improve the fatigue crack growth resistance of these low-cost steels in high-pressure hydrogen gas? And so I just want to ask a few questions about what are the types of questions that we might have to ask and address to see if we can improve this resistance to intergranular fracture in the presence of hydrogen. And one of the ideas that I wanted to propose is, does the cyclic deformation somehow interact with these grain interfaces to help enable the intergranular fracture in the presence of hydrogen? So if we were to apply a force or a displacement to these metals, that force and displacement can only be accommodated for so much by the elastic stretching of atomic bonds. And eventually, if we need to accommodate more displacement, we have to generate and propagate defects, these crystal defects. And a lot of times, the nucleation and propagation of these crystal defects can happen in very discrete bands. And if these bands of plastic deformation, as we call it, intersect with grain boundaries, these can form stresses locally. And so we can get elevated local stresses acting in concert with the remote stress to enable the fracture of these, to enable cracking along these grain boundaries, especially in the presence of hydrogen. And so I wanted to propose that perhaps we can investigate the interaction, particularly of the deformation formed under cyclic loading, with these interfaces. And can we apply modern tools like crystal plasticity modeling to try to actually quantify these elevated stresses if they exist at the intersection of deformation bands with these grain interfaces? And as Professor Ritchie mentioned this morning, the deformation metals can actually be enabled by hydrogen. And so this is one of the research areas that was pioneered at the University of Illinois by the late Howard Birnbaum and was continued by Professor Ian Robertson and Professor Safranis. And so do we have in these steels hydrogen-facilitated deformation? And is it possible that this hydrogen-facilitated deformation acts in concert with this hydrogen-enhanced decohesion at grain boundaries, so that these 2 mechanisms, as Professor Ritchie said, are acting synergistically instead of competitively? This is a relatively new idea, I think, in the hydrogen embrittlement community, and one that we proposed in a recent publication last year. And so another possibility that we need to consider are there impurities, chemical impurities, alloy impurities in these steels that segregate to the grain boundaries that can be enabling this intergranular fracture? So it's quite widely accepted that impurities such as phosphorus and sulfur in steels can segregate to grain boundaries and could enable intergranular fracture, particularly in the presence of hydrogen. So the phosphorus and sulfur and hydrogen could all be acting to weaken the bonds at these grain boundaries and to allow cracks to propagate along these grain boundaries. And so can we characterize the composition of these grain interfaces especially using modern analytical methods. There's a lot more analytical tools we have at our disposal now to try to address these types of problems than we did 20 years ago. And then can we, if we were able to identify perhaps the presence of some of these impurities on the grain boundaries, can we do something to mitigate the presence of these impurities on the grain boundaries? Can we develop steels with so-called clean interfaces? And there's a very, very intriguing set of data that was generated by Professor Charlie McMahon at the University of Pennsylvania in the late 70s and early 80s that I don't think has ever been really fully exploited or fully digested to see if it has merit in pursuing some of his ideas. And what Professor McMahon particularly did with this plot is he looked at steels with different compositions of phosphorus, sulfur, manganese, and silicon. So each one of these data points represents a steel with a different composition, varying those 4 elements. And in this plot, he's got some weighted average of these alloying elements. And on the y-axis is a measure of the hydrogen-assisted fracture resistance. And you can see that at some point, these this parameter, the hydrogen-assisted fracture resistance, starts to increase quite dramatically. And what Charlie found is that the 2 elements that were most important were the manganese and the silicon. And the way I understand Charlie's papers is that it was still the phosphorus and sulfur which could enable the intergranular fracture, but somehow it was the manganese and silicon which was helping these elements segregate to the grain boundaries. And I don't think Charlie ever really fully understood this or explained it. So I think this is a really rich area that we could try to look into. And finally, one question I think we can ask is, can the interface structure, just the intrinsic interface structure of these grain interfaces be modified to improve the resistance to hydrogen-assisted fracture? And one of the prompts for me to ask this question was some work that Professor Ritchie and I did with some of his students and also a colleague of ours at Lawrence Livermore National Lab. And what we did is we looked at just a nickel 201. And our colleague at Lawrence Livermore was able to process this nickel 201 to change the grain boundary structure. So basically to change the atomic registry of certain grain boundaries. And these are the materials that have this high registry across the grain boundaries we call this high special boundary fraction. And this low special boundary fraction has grain boundaries that don't have as much atomic registry. And what we're plotting here on the y-axis is the fraction of intergranular fracture in these nickel alloys after they're exposed to hydrogen versus the hydrogen concentration. And indeed, these boundaries that have more atomic registry have less intergranular fracture. And so is there some other way that we can try to manipulate just the intrinsic structure of grain boundaries in steels to mitigate the hydrogen-assisted intergranular fracture? So I wanted to change the emphasis of this talk just a little bit. Instead of talking about these intrinsic variables that we consider, these intrinsic metallurgical variables to try to mitigate hydrogen-accelerated fatigue crack growth in steels, I wanted to ask a question about, are there some extrinsic mechanisms that we can consider and explore for trying to mitigate hydrogen-assisted fatigue crack growth in these ferritic steels? I want to draw your attention first to this plot, which is from John Holbrook when he was at Battelle, Columbus in the mid-'80s. And what John did was he measured the fatigue crack growth rates of another pipeline steel. And what he did was he mixed different amounts of carbon monoxide in the hydrogen gas. And so this is the percentage of carbon monoxide and hydrogen. And as you can see, as the percentage of carbon monoxide and hydrogen increases, the crack growth rates are coming down quite dramatically, so that they're almost at the point where at the same magnitude of crack growth rate as if the measurement was done in an inert gas. And so the notion of what can happen with some of these gas inhibitors in hydrogen gas is that species like carbon monoxide or oxygen can dissociatively absorb on the surfaces of these steels, which can prevent the adsorption and dissociation of hydrogen. So there's this competitive adsorption and dissociation between some of these impurity species and hydrogen. So that basic notion was illuminated quite well, but it's in a rather obscure report from Battelle in the mid-'80s. But I think there's more that can be done here. In particular, one of the notions I would think would need to be explored is what is the interaction of deformation, let's say, at a crack tip with this competitive adsorption between hydrogen and oxygen, and could there be some sort of frequency effect on how fast we're applying loads? And more importantly, can we include some of these effects of inhibitors in modern crack growth models? And so this is my summary, and the main point I was trying to make here is from a technology perspective is that hydrogen accelerated fatigue crack growth is a very important safety consideration for low-cost ferritic steels. And then one of the common threads that I wanted to show in these slides is I think a lot can be done just with trying to better understand interfaces, and whether that's the interaction of cyclic deformation with grain boundaries, the presence of possible presence of alloy impurities on grain boundaries, the structure of grain boundaries, and also perhaps the competitive absorption of hydrogen inhibitors on free surfaces. Thank you.
Thank you, Dr. Summerday. I think given the late hour, we'll ask people, yes, there's a question.
Anybody except Rob.
Brian, from the perspective of trying to inhibit or slow down hydrogen growth, one thing we tried years ago was putting in retained austenite, having films of retained austenite. And with a ferritic steel, you could do that by some kind of two-phase heat treatment.
So you did this just in fatigue?
No, we didn't do it in fatigue. We did it in hydrogen cracking.
Oh, you did?
Yeah, and we got a big effect. We dropped by about and we argued it was associated with the diffusion of hydrogen being much slower through the austenitic layers.
So you basically had a two-phase material.
But there wasn't much retained austenite. It had quite a big effect. But with the ferritic steel, you could get quite a
yeah, that's an intriguing idea, Rob. So do you remember what volume fraction you had?
It would be very small, because it would be retained austenite coming from a heat treatment. So it would be a few percent in our case. But you could get 10, 20% in the ferritic steel if you wanted to.
Yeah, that's an interesting idea, Rob. Thanks.
One more question.
Brian, those results that you've shown by Holbrook, I think they are impressive results.
They are.
And if I recall well, they have to do with saturated or unsaturated chemical compounds. Am I right? If the compound there that he uses, for instance, if it is CO2, then it is, CO is an inhibitor, but I think he also used CO2.
But he found no effect with CO2.
No effect.
Yeah.
So is there some chemistry that is worth pursuing here at I²CNER, for instance, and see what happens with the chemistry there? Why the unsaturated compounds, for instance, do inhibit, whereas the saturated compounds do not?
I completely agree with you. And in fact, we could engage your chemistry colleagues at Illinois and here at Kyushu. So I think there's an opportunity for some interdisciplinary work between the thematic areas, especially on that particular issue. And maybe also just the segregation of impurities to grain boundaries as well. So I think there's a lot of basic chemistry here that would promote perhaps some interdisciplinary interactions between the thematic areas.
Okay, thank you. Yeah, we'll do it.
No, we have one more question. We have all the directors trying to keep us from having our break. Okay.
That's their prerogative, right?
It is.
I would like to make this very short question. From the future science, future side, I was really surprised that sulfur and phosphorus can also segregate into the grain boundaries, because we know that these are a strong poison for the polymer electrolyte fuel cell and also very strong poison even for the high temperature fuel cells. My question is, can such segregated sulfur and phosphorus get diffused through the grain boundary into the surface of the stainless steel, for example?
So as your question is, does it diffuse to the lens?
Yeah, to the surface.
To the free surface?
Yes.
I'm sure it does.
Oh.
If it diffuses to the grain boundaries, I'm sure it diffuses to the free surface as well.
Yeah. Because that could be very important point from the technological point of view. And we have also found some poisoning effect, even for the high temperature fuel cells. Yeah. Thank you very much.